This is a Newtonian physics engine that simulates the movement of neutrons in spacetime. It ignores nuclear forces and nuclear decay, and also electromagnetism, hence the lack of charged particles. There's also a black hole at the center of the lines. This universe is programmed using some pretty simple code that's probably horrifying to a software engineer. There's global variables, repetition, and nested conditionals, but it's the thought that counts, right? Oh, and you should also know that because the animation software I use does not accept pandas, the first way I got it to work was by storing the velocity, acceleration, and position data on a frame-by-frame basis in separate CSV files, for a total of 5,000 CSV files for a 5,000 frame animation. And perhaps the only part of this code that a software engineer might admire is I left it working the first way I found it to work. This isn't just a Newtonian physics engine. It's the beginning of a larger project to create an accurate universe simulation which, as a field, I think, is the dark horse candidate to kickstart the singularity through emergent intelligence. All the large dots in the simulation represent neutrons when the universe was just thousands of years old. The neutrons begin in a relatively small clump and over time spread out over a great distance. Change some of these neutrons to protons and electrons, along with their corresponding properties, and I see no reason that molecules wouldn't arise. You can't zoom in on any one of these simulated particles like you can in real life. If you wanted to, there'd need to be quantum physical calculations every time you looked. This method, simulation focus, could be applied by slowing time elsewhere in the simulation and utilizing different non-Newtonian physics calculations locally. This way, unless the non-Newtonian physics was relevant, such as in a supernova or in an atom splitting, reality could be accurately simulated without requiring the vast amounts of energy, time, and resources to actually copy reality. Simulation focus doesn't just mean computational resources can be proportioned to what matters. It also solves the paradox posed by Michio Kaku.
From an engineering perspective, may be impossible to build.
Yes, no computer can build a universe capable of simulating the entire universe, except the universe itself.
So that's your intuition, that our universe is very efficient, and so there's no shortcuts.
Right. Two reasons why I believe the universe is not a simulation. First, the calculational numbers are just incredible. No finite Turing machine can simulate the universe. And second, why would any super intelligent being simulate humans? If you think about it, most humans are kind of stupid. I mean, we do all sorts of crazy, stupid things, right? And we call it art. We call it humor. We call it human civilization. So why should an advanced civilization go through all that effort just to simulate Saturday Night Live?
Well, that's a funny idea, but it's also, do you think it's possible that the act of creation cannot anticipate humans? You simply set the initial conditions and set a bunch of physical laws, and just for the fun of it, see what happens. You launch the thing, so you're not necessarily simulating everything. You're not simulating every little bit in the sense that you could predict what's going to happen, but you set the initial conditions, set the laws, and see what kind of fun stuff happens.
Well, in some sense, that's how life got started.
There are a lot of parts in the universe, and if we could only see the Big Bang, we'd know all the parts. The Planck epoch, the beginning of the universe within the Big Bang theory, saw all the universe expand from the size of an atom to a grapefruit in literally the tiniest fraction of a second possible. 1 microsecond minus that fraction later, a relatively long time at that point in time, the first protons and neutrons began to form. Hadrons could get along fine thanks to weak force, strong force, and gravity, and there were clumps of protons and neutrons forming nuclei all over the place. But it was another 380,000 years before hadrons learned to get along with leptons. That is, electrons began to orbit nuclei. Hydrogen and helium atoms have been born, and the rest is history. The electron and the hadrons are some of the most resilient, independent arrangements of matter to have ever existed. They're as independent as one can get in a universe where everything is connected and there is this constant circle of life. Despite our bodies being made up entirely of the stuff, the rocks, plants, air, and planets too, each individual proton, neutron, and electron in the universe is about as old as the universe itself. The only thing older than protons, neutrons, and electrons are the things that make these particles up, which is ironic considering the food we eat as people is far younger than us. Molecules, atoms, and nuclei come and go, but the particular neutrons, protons, and electrons never go unless they're annihilated in something like a large hadron collider or at the center of a star. Furthermore, if you've ever heard of E equals mc squared, or if you've ever looked at the sun too long, you know these things have huge amounts of energy. and they want to blow up in a big, blinding, blow you away kind of way. The universe was hot, 100 million degrees hot when these things first appeared, which meant they were absolutely flying in every direction at beyond blistering speed. And all that energy meant that despite there being these fundamental forces that draw matter together, it was just plain difficult for mass to stick together because everything had such tremendous momentum. Matter found a way to settle down, though, into relatively enormously heavy arrangements fairly rapidly. To reiterate, in a microsecond, the first protons and neutrons formed, whereas the electron got there even earlier. At the time, these hadrons were the heaviest things to have ever existed. They were like black holes that wouldn't and didn't quit all the way up until today when we smashed them together using magnets, the world's greatest minds, and billions of dollars, in a tunnel 100 meters underground near Geneva. It wouldn't be until 380,000 years later, after the Big Bang, before matter found a heavier, denser, albeit less resilient way to arrange itself. That subsequent arrangement would be the periodic table of elements, which, all in common, consist of matter. There is no elemental spacetime on the periodic table, even though from a linguistic perspective there should be, so they're not dictionary definition elemental. The elements are better thought of as fleeting phenomena that, aside from literal black holes, are the densest, heaviest arrangement of matter known to humanity. Elements are always young, though. Each drop of water was sand not long ago. Being the precursor to life as we know it, one might assume that a universe simulation ought to begin with elements. The problem with the elements is it's a way of looking at matter as well over 100 and growing different kinds of things. Each element has its own properties, its own rules and behaviors. It's similar to looking at matter through the Standard Model. Through the Standard Model, there are 17 and growing different kinds of things. On top of this, we don't even know how they all interact. These lenses through which to see the universe are incomprehensive and incomplete. But then you have this beautiful, elegant, simple way of looking at matter. The proton, neutron, electron, say echelon, dominated the universe from 1 microsecond until the universe was 380,000 years old. To this day, protons, neutrons, and electrons make up everything. It is truly ironic that something so small, so normal, so plentiful and boring can be so immortal. Everything significant to the emergence and day-to-day of life is made up of protons, neutrons, and electrons. The other stuff, the neutrinos, the wandering fermions and leptons one might find in a black hole, the center of stars, or within CERN, these things are perhaps totally insignificant to life as we know it. It is incredibly rare for a proton or neutron or electron to ever break apart, and this is why life has learned to deal with this arrangement of matter. These are universal constants. That's why this physics engine ignores quantum mechanics, because while quantum mechanics are essential in particle colliders, nuclear bombs, and building nanoscale transistors, it might literally be insignificant when simulating a universe to produce emergent life. The outline of my proposed universe simulation is as follows. 1. Simulate universes, saving injection vectors and the behavior of the simulations. The injection vector is the acceleration, velocity, position, and quantity of point masses when the universe simulation is instantiated. The behavior is the acceleration, velocity, position, and the quantity of point masses over the lifespan of the simulated universe. The point masses can only have 3 sets of properties. They can be electrons, protons, or neutrons. 2. Learn from the data. Initial questions might be, how do injection vectors correlate with the lifespan of the universe? What injection vectors correlate with harmony and equilibrium? That is, repetition, patterns in the data. What injection vectors correlate with indicators of self-replication, such as the point masses in an arrangement or equilibrium changing, but the arrangement or equilibrium retaining some sort of consistency? 3. Apply algorithms to the selection of injection vectors. 4. Add simulation focus. Use conditionals to include or exclude branches of physics. Why bother simulating quantum mechanics when the location of interest in the simulation has no free elementary particle? 5. Create emergent intelligence. Optimize the accrued computational power required for vast universe simulations to be an object-oriented environment for emergent intelligence. Solve death and drudgery, discover all there is to discover, see the past, present, and future exactly as they were, are, and will be, by benchmarking the objects in the environment to behave as similarly to objects in our own environment as possible. Another bit of irony is that the world's smartest people, the people capable of programming artificial intelligence, which is everyone's best guess and favorite for what will kickstart the singularity, are all focusing on alchemy as opposed to an exhaustive algorithmic mathematical search for simulated life. Physics simulations are getting better and better, whereas artificial intelligence has pretty agreeably hit a plateau. There's no doubt that potentially the quickest way to kickstart the singularity is intuitive conception. And it's not that intuitive conception even seems remotely impossible, but coding complex brain-like logic seems kind of hopeful and perhaps hopeless. I'm amazed all the time by what modern artificially intelligent software can do, particularly natural language processing and robotic control. But it's kind of like Nick Bostrom's simulation theory, which says that since humanity is the only known intelligent life, the other intelligent life likely behaves similarly to human beings. There are no other examples of what intelligent life acts like other than ourselves. So why shouldn't this same forward-thinking hypothesis function in reverse? The only way we know for sure that intelligence can emerge is through evolution, through mass and spacetime, through matter taking the form of increasingly lifelike arrangements. Whereas why does anyone think a team of software engineers with access to a supercomputer could ever code a brain? Artificial intelligence might mean building intelligent machines through the use of conditionals, recursion, and logic, but only means that because that's what the guy who coined the term was working on. AI, to me, means artificial life. If you are more interested in kickstarting the singularity than becoming rich, consider machine learning as only a step and not the answer.